You're standing at the edge of a shoreline that hasn't existed for millions of years. The sea is shallow, warm, and murky with silt, scattered with shapes both familiar and foreign. You're not really there, of course. But imagine it anyway. This isn't about action, it's about atmosphere. The kind that drifts in like fog and never really lifts. We're going back roughly 60 million years. Not to see the megalodon just yet, but to squint at its long evolutionary shadow. See, when people talk about Carcharocles megalodon, they usually think of the massive, iconic predator that lived later. But if you want the full story, you've got to start with the quiet stuff, ancestors. Mislabelings. Things shifting just a bit from one generation to the next. Let's begin in the Paleocene, shortly after the dinosaurs took their leave. The ocean's predators were starting fresh. Sharks, of course, had already been around for hundreds of millions of years. Older than trees, older than bones, really. But the extinction event that wiped out most of the big reptiles left a power vacuum in the seas. Some fish got bigger. Some reptiles tried their luck. And certain sharks, slow and steady, began to drift into something new. There was Otodus, for instance. Not flashy, but important. Otodus is the genus most paleontologists now agree links directly, or indirectly, to Megalodon. These were early mackerel sharks, blunt snouts, large eyes, strong tails. They weren't Megalodon, but they had the attitude, if not the size. Fossils date them as far back as 60 million years. Their teeth were already large. Thick roots, triangular crowns. Serrations came later. What this really means is that before you ever had Megalodon, you had a lineage slowly testing the waters. Bit by bit, generation after generation, sharks were experimenting. Not consciously, just in the evolutionary sense, surviving long enough to pass along some slightly better trait. A tooth that cuts a little deeper, a jaw that opens a bit wider, a muscle twitch that gets you to prey 1 second faster. But here's the thing. None of this happened fast. Not even remotely. You're looking at glacial shifts stretched across epochs. If evolution had a tempo, this part would be a dirge. And that's perfect for us. Over the next few million years, Otodus gives way to Carcharocles auriculatus. This is where it starts to look familiar. Auriculatus had teeth nearly identical in shape to what you'd expect from a megalodon, just smaller, less refined. Still, this was a shark that could grow over 30 feet long. That's not small. But it's still not the 60-foot giant we're headed toward. This was around the Eocene, somewhere between 55 and 34 million years ago. The world then was different, but not dramatically so from the Miocene ocean's megalodon would later dominate. Warm seas. Lots of shallow coastal zones. Massive schools of fish. Early whales, slow and stubby. And right in the mix, these large sharks with blades for teeth. It was a testing ground. Carcharocles had a particular evolutionary trick: serrations. Their teeth developed tiny ridges on the edges, like steak knives, not daggers. These helped shear through flesh and bone. That change alone marks a pivotal shift. A smoother tooth is good for grabbing, but a serrated tooth? That's made for slicing. And that's how you start climbing toward the megalodon model. It wasn't just size. It was style. See, auriculatus and its close successors, see, angustodons, see, chubutensis, all form a gentle slope on the megalodon family tree. Their teeth get broader. Serrations get cleaner. Crowns widen. Root structure stabilizes. Each trait you'd expect in a giant predator shows up first in something smaller, quieter. Fossils from these transitional sharks show up all over the place. Southeast US, North Africa, South America, New Zealand. Teeth buried in sediments that hardened into sandstone and marl. What you're seeing in the rock record is not just distribution, it's potential. These sharks weren't locked into one niche. They were exploratory. Not consciously, again, just biologically adaptable. Even the naming gets murky. Paleontologists used to place Megalodon in the same genus as the great white, Carcharocles. But the more they looked, the more they saw that Megalodon didn't evolve from white sharks at all. It followed its own branch, one that started long before the great white ever showed up. So, They moved it into Carcharocles. Others argue for Otidus still. It's a semantic drift, but a meaningful one. You can fall asleep thinking about that. Generations of taxonomists debating Latin names for creatures that haven't swum in 3 million years. Imagine being that committed. Anyway, these ancestral sharks weren't invincible. They faced changes in sea level, temperature swings, and shifts in prey availability. But they didn't go extinct. They adjusted barely. They weren't evolving rapidly. They were inching along the slow curve of survival. Imagine one of them now. You're hovering over an Eocene sea shelf, maybe near what is now the coast of Morocco. Below, a 30-foot sea auriculatus glides through green water, scanning for sluggish fish or small whales. Its body language is patient, deliberate, nothing frantic. This is not a shark that sprints, it paces. You could probably watch it for hours and not see it attack. It doesn't need to. These sharks didn't hunt often. When they did, it was sudden, brutal, efficient. But most of the time, they drifted, conserving energy, trusting that eventually something slow and edible would cross their path. That's the rhythm of these early giants. Not speed, endurance. Not aggression, presence. The fossil record shows us enough to know that by the late Oligocene, around 23 million years ago, these transitional sharks had evolved into something very close to Megalodon. Carcharocles chubutensis is usually seen as the last stop before the main event. Its teeth could exceed 5 inches long. Body size estimates start pushing into 45-foot territory. At this point, you're not far off. Just a few more tweaks. So what changed? Nothing sudden. No dramatic jump in size or power. Just incremental shifts. Each shark a little better suited than the last. Until eventually, one of them looked like Megalodon. The world had no idea. But the ocean was about to crown a very large, very quiet king. And it didn't roar. It just was. You could fall asleep to that kind of confidence. You're looking at a tooth. Not in your hand, just in your mind. Imagine it. Maybe 4-5 inches long, roughly triangular, with edges so fine they still feel sharp after millions of years buried in rock. The root is thick, rugged. The enamel is pale gray, maybe tinged with orange or brown depending on the minerals in the soil. It's not just a fossil. It's a clue. And it's basically all we have. Here's the thing. Almost everything we know about Megalodon comes from teeth. Sharks don't have bones like you do. Their skeletons are made of cartilage, light, flexible, great for swimming, terrible for fossilizing. So when a Megalodon died, its body mostly dissolved into nothing. But the teeth? Those stuck around. One shark might go through 20,000 to 30,000 teeth in a lifetime. They lost them constantly, like confetti, but dangerous. And that's what fills the fossil record, layer after layer of ancient seabeds studded with shed teeth. Single teeth, partial rows, a rare vertebral column here and there, but mostly just teeth. Entire evolutionary timelines written in enamel. Let's break that down. First, the size. Megalodon teeth are the largest shark teeth ever found, some over 7 inches long. That's not just large, that's absurd. Even a big great white tops out around 3 inches. These things weren't just for show. Their sheer width and depth suggest a bite capable of crushing ribs, splitting vertebrae, and shattering bone. And they're everywhere. You can find Megalodon teeth in places like Florida, the Carolinas, Peru, Morocco, and even parts of Europe and Asia. Anywhere there was once a warm, shallow sea, there's a chance a Megalodon dropped a tooth. Beachcombers still find them today, washed up from ancient sediments or dredged out of rivers. No digging required, just patience and the right coastline. Now think about that. You're walking along some modern shoreline, and you find this thick, triangular tooth in the sand. A fragment of a predator that hasn't existed in 3 million years. A dead thing that once hunted living things and now rests in your palm. That's eerie. That's cool. But mostly, that's informative. Because every tooth tells a story. Look close. The serrations on the edges? Fine and even in earlier megalodons, worn down in older individuals. The base, broad and strong, hints at massive jaw pressure. Some teeth even show bite marks, maybe from failed kills or fights. You can see where growth lines formed, like rings in a tree. They don't just say shark. They say how old, how big, how effective. Paleontologists use these teeth to estimate size. There's a formula. You take the height of the tooth and run it through a model based on known shark jaw proportions. Is it exact? But it gets you close. A 6-inch upper anterior tooth? That's probably from a shark around 50 feet long. 7 inches? You're pushing 60. Bigger than a school bus. Twice the length of A to Rex. Then there's context. Teeth don't fossilize in a vacuum. They show up in layers. And those layers tell you where in time you are. Most megalodon teeth are found in Miocene and Pliocene sediments, about 23 to 3.6 million years ago. Earlier versions, like C. chibutensis, show up in slightly older layers. By looking at which teeth appear in which strata, you can map the evolutionary slope from ancestor to apex, and then the slow fade into extinction. Some layers are rich with teeth, others barely a trace. That's meaningful. It tells you where the shark lived, fed, gave birth. And just as importantly, where it didn't. Then there's color. Fossil teeth aren't always black. Some are gray, brown, even bluish. That has nothing to do with the shark. It's about the sediment they were buried in, the minerals that seeped in and replaced the organic material over millions of years. Iron oxide gives red tones. Phosphate-rich soils produce black. It's a geological palette, and every tooth is a tiny painted fossil. You can even see pathologies. Some teeth have deformities, twists, notches, stress fractures. These might be genetic flaws, or signs of jaw injuries, or where from chomping too hard into something solid, like a whale skull. Some rare teeth have puncture marks. That's especially interesting. It suggests interspecies conflict, possibly even cannibalism. Young megalodons were vulnerable after all. A big one might have snacked on a smaller one. It's not polite, but it's effective. Let's not rush past that idea. Everything we know about megalodon biology, diet, growth, behavior, filters through teeth. There are no stomach contents to study. No preserved jaws. No complete skeletons. Just rows and rows of teeth. And that's okay. Because teeth are honest. They don't lie. They don't rot. And they show up everywhere. You'll find museums packed with megalodon teeth. Some are polished, others kept raw. Some arranged in fake jaws, others left as loose fossils. The biggest ones usually get center stage. But the smaller ones? Those are often from juveniles. And they matter just as much. Because juvenile megalodons tell us about nursery habitats, shallow coastal zones where they were less likely to get eaten and more likely to find easy prey. Where you find lots of small teeth in one layer, that's probably a nursery. And where you find big ones mixed with large whale bones, that's likely a feeding ground. It's almost boring how straightforward it is. But that's what makes it useful. There's one more detail worth pausing on, the transition teeth. The ones that don't quite fit the textbook megalodon mold. Some are from the borderline species, C. chibutensis, C. angustidens, sharks that lived before the true megalodon emerged. Their teeth are similar but different enough to mess with neat timelines. Slightly different serration angles. Narrower roots. Sometimes even a lingering cusp at the base, inherited from older ancestors. These teeth are like blurry snapshots in an old family photo album. Not quite this, not quite that, but clearly part of the line. And sometimes, even paleontologists disagree on which shark a tooth belongs to. That's how subtle some of these differences are. A few millimeters off in root angle and suddenly you're arguing genus definitions. That's science. That's paleontology. That's where the lull sets in. You'll fall asleep somewhere in that debate, right between definitely megalodon and probably something close. It's a strange comfort knowing that such a massive animal left behind something so small. A piece of itself, repeated thousands of times, across oceans and epochs. Not a full body. Not a voice. Just teeth. That's what survives. That's what tells the story. Picture this. A lineage of sharks slowly gaining size, generation after generation. No rush. No big leap. Just incremental shifts, stretched over millions of years. Now you're at the point where those shifts start to matter. Where big becomes very big. This is where the rise of the giant mouth really begins. You've already met the ancestors, Otodus, Carcharocles auriculatus, C. angustidens, C. chibutensis. But now we're standing at the inflection point. Somewhere in the early Miocene, about 20 million years ago, something shifted, not suddenly, but clearly. The descendants of those earlier sharks started getting huge. Not metaphorically. Literally. This is when we first start using the word megalodon without the qualifiers. Let's take it slow. Why get big in the first place? Because the ocean was full of meat. Specifically, whales. The Miocene and Pliocene epochs were boom times for marine mammals. Baleen whales, toothed whales, beaked whales, dolphin-like forms. Some slow, some fast, many with few defenses beyond size and numbers. And if you're a shark with serrated teeth and a growing frame, that's a buffet. A high-calorie, high-efficiency hunting zone. Early megalodons had every reason to grow, and nothing in their path saying, don't. No larger predators. No evolutionary constraints on scale. No major gaps in prey availability. Just open ocean and opportunity. Over time, larger individuals simply outcompete smaller ones. They could take down bigger prey, travel farther, store more energy. So the genetic trend leaned upward, tooth by tooth, bite by bite. Now, growth like this doesn't happen randomly. It follows patterns. Sharks are indeterminate growers, meaning they grow their whole lives, just more slowly over time. But there's still a cap, an evolutionary average. And in megalodon's case, that cap crept upward over the millennia. From 30 feet to 40, then to 50. Some outliers hit 60 feet or more. Not a guess, a reasonable projection based on tooth size and jaw modeling. Here's where things get fun, or at least methodical. Paleontologists use dental formulas and known growth curves to estimate body length. You take the largest anterior tooth, usually from the upper jaw, and plug it into equations based on comparable modern sharks. It's not perfect, but the models agree on this much. Megalodon was an absolute unit. Not just long, but bulky. A shark like that wasn't streamlined for speed like a mako. It was built for power. Think of it as a slow torpedo made of muscle and teeth. Most reconstructions peg its weight at 50 to 70 tons. That's whale territory. And yes, it likely fed on whales. Coincidence? Not really. Its mouth alone could have been over 9 feet wide. That's not metaphor. That's geometry. A full-grown megalodon could open its jaws wide enough to swallow 2 adult humans side by side. Not that it would. It had other things on the menu, but it could. Now imagine that mouth at work. It didn't nibble. It crushed. Bite force estimates are in the range of 24,000 to 40,000 pounds per square inch. That's enough to crack through a whale's rib cage like a breadstick. Not graceful, not elegant. Just overwhelming force. That's how you feed when you're 60 feet long. You kill once and eat for days. But let's not glamorize this too much. Remember, you're trying to fall asleep. So think about the slowness of it. A shark that big doesn't dart around like a barracuda. It glides. Conserve energy. Approach. Strike when the angle's right. Then drift back into the blue, blood trailing in the water, prey slowing, dying. No panic. No chase. Just inevitability. Now zoom out. Where did this happen? All over the world. Megalodon wasn't local, it was global. Fossils show up on every continent except Antarctica. That tells you something. This shark wasn't tied to a single environment. It went where the whales were. Where the water was warm. Where there was room to roam. Its range likely extended from coastal zones to the open ocean. It could cruise for miles. Maybe thousands. Probably followed migration routes, prey patterns, seasonal temperature shifts. Think of it as the original long-haul predator. Not fast, but persistent. Always somewhere, always watching. Here's another thing. The size wasn't just for hunting. It was for survival. Large animals lose heat more slowly. That's called gigantothermy. It means Megalodon may have maintained a slightly elevated body temperature, letting it hunt in cooler waters without going sluggish. It also means it could give birth to large young, probably 10 to 13 feet at birth, based on neonatal teeth. That's absurd. A Megalodon pup was the size of a great white adult. From day one, it was already too big for most predators. That's not a coincidence. That's selection pressure. Bigger babies had a better shot. So that's what evolution favored. You're probably wondering what they looked like. Truth is, we don't know for sure. Soft tissue doesn't fossilize well. Artists often render Megalodon as a scaled-up great white, but that's just convenience. It may have been bulkier, broader snout, different tail proportions, maybe a darker top side for camouflage. But whatever the case, it didn't need flair. Size was enough. So how did it live? Not in schools. Probably solitary. Maybe came together to breed, maybe not. Most large predators don't tolerate competition, and a Megalodon likely didn't need help taking down prey. It would have used ambush tactics. Swim below, strike from beneath. One massive bite, then wait. Follow the injured animal until it bleeds out or slows down. Efficient. Methodical. But here's the core of it all. That rise wasn't dramatic. It was boring. Gradual. Predictable, even. Fossil teeth get a little bigger. More refined. Spread over wider areas. You don't get a single moment where Megalodon arrives on the scene. You get a slope. A steady uptick in size and reach. And that's why it worked. Because nothing tried to stop it. No rivals. No environmental barriers. Just a shark getting better at being huge. But nothing stays perfect forever. That part comes later. For now, just picture the slow, steady arc of evolution giving rise to a creature that didn't sprint or leap or dazzle. It just existed, massively, across oceans and centuries. And in the silence beneath the waves, a mouth 6 feet wide opens once more. Close your eyes and imagine the stillness of deep water. Not the bottomless abyss, the middle depths. Not too dark, not too light. Just suspended blue. Now put a whale there. Something slow. Maybe a primitive baleen whale, about 25 feet long, cruising through warm Miocene seas. It's not in a rush. It doesn't expect danger. Why would it? There's nothing out here that big. At least, that's what it thinks. But Megalodon is nearby. Not lunging. Not circling. Just there. Gliding as it does. Measuring. Waiting. And that brings us to the core behavior of this entire creature. How it fed. How it survived. How it ruled. You're not going to get a flurry of attacks or dramatic standoffs. What you're going to get is a series of deliberate, brutal bites, and a lot of drifting in between. Because here's the truth about Megalodon's feeding. It was efficient. Boringly so. Start with its prey. By the time Megalodon had reached peak size in the mid to late Miocene, around 15 to 10 million years ago, the oceans were bursting with whales. Evolution had cranked out a whole range of them. Some were slow baleen types, early ancestors of modern humpbacks and fin whales. Others were toothed and aggressive ancient sperm whales, early dolphins, even now extinct predatory cetaceans like Livyatan, which had their own massive teeth. But Megalodon didn't need to chase the fastest or fight the toughest. It likely targeted the slow, the weak, the young. It was a strategy of minimal effort, maximum reward. That's what the fossil record shows, anyway. Whale bones with bite marks. Vertebrae with huge tooth gouges. Ribs split down the middle. Sometimes even signs of scavenging, not hunting. Megalodon showing up late to a carcass and taking what it wanted. Think about the biomechanics for a second. With a bite force pushing 40,000 psi, Megalodon could shear a whale's flipper clean off. One bite, and the prey's ability to maneuver would drop to near zero. Another bite, and major organs would be exposed. The shark wouldn't need to kill instantly. It could maim, retreat, and wait for the bleeding to do the rest. This wasn't about speed. It was about certainty. Now let's talk targeting. The most logical strike zones were the flippers, tail stalk, or lower spine. Fossil whale remains with bite marks in these areas suggest Megalodon knew what it was doing. Cripple the whale. Let it tire. Move in for the finish. Some theories suggest it may have even used a hit-and-run tactic. Strike once, then disappear. Let the whale panic. Slow down. Then return. No wasted energy. No risk of injury. Just dominance, one step at a time. Now don't confuse this with laziness. This is strategy. Large predators don't gamble. A 60-foot shark can't afford to miss. So every move had to count. And this brings us to feeding frequency. How often did Megalodon need to eat? That's tricky. Estimates vary, but some paleontologists think a large megalodon could survive weeks on a single kill, especially if it was a full-grown whale. That's thousands of pounds of meat, fat, and bone. Plenty of energy. Plenty of insulation. So it wasn't feeding daily. Maybe not even weekly. It was a roving apex predator that needed volume, not frequency. That changes how you picture it. Not constantly hunting. Just drifting. Waiting. Watching. And occasionally striking. There's something sleep-inducing about that rhythm, isn't there? Long stretches of stillness. Intermittent bursts of motion. Like the ocean itself. Like the story we're telling. Now, here's another layer. What did Megalodon's bite actually do? Let's get anatomical. Those serrated teeth weren't there for looks. They acted like saws. When the shark bit into a whale, those ridges would slice through flesh and connective tissue with less resistance. Like a bread knife, not a chef's knife. The serrations increased cutting efficiency and helped grip slippery muscle fibers. This mattered, especially with moving prey. The teeth were arranged in rows, maybe 5 to 7 working rows at any time, with replacements constantly developing behind. A lost tooth wasn't a problem. Another was always ready to rotate forward. That conveyor belt system is common in sharks, but in Megalodon, it was scaled up to monstrous proportions. Now let's talk energy. Every kill wasn't just about survival, it was about fuel for movement, for growth, for reproduction. A big Megalodon needed huge energy reserves to power its massive muscles, to maintain internal heat, to cruise for long distances. Some studies suggest it might have had a partially endothermic metabolism. Not warm-blooded like a mammal, but able to regulate internal temperature enough to keep hunting in slightly cooler waters. That would have expanded its range, given it more prey options. Let it travel farther between meals. But again, don't picture a roaming madman. Picture a slow, thoughtful tank. It could cruise for days, weeks, across ocean basins, waiting for the right moment. And when it came, one bite, maybe two, then calm again. There's something almost meditative about that. Let's bring in the food chain. Where did Megalodon sit? Right at the top. No known predator hunted it. Not adults, anyway. Maybe the very young were vulnerable. Other sharks, even other megalodons. But once it reached full size, it ruled. It wasn't part of the food web. It defined the food web. Marine ecosystems at the time bent around its presence. Some prey species evolved larger bodies or group behaviors to survive. Others may have shifted migration patterns. The presence of a superpredator reshapes everything below it. But eventually, the pressure starts to reverse. The prey begin to change. Get faster. Get more agile. Group up. New predators emerge. Competitors. And Megalodon's slow, overwhelming style? It starts to falter. But we're not there yet. Right now, in this part of the timeline, Megalodon is in its prime. The whales are plentiful. The waters are warm. The sea is full of opportunities. The kill is easy. The days are long. And the shark, massive and slow, is simply feeding. Occasionally. Methodically. Without panic. Without effort. And then, it disappears back into the blue. Drift with it for a minute. You're in open water now, far from any coast, no seafloor in sight. The sunlight only reaches so deep, then fades into pale gray. All around, warm currents. Not turbulent, not cold. Just vast stretches of temperate, nutrient-rich ocean. This is where Megalodon spent much of its life. Roaming. Not in tight circles, not near reefs or coral beds. This was a wide-ranging animal. Global, not regional. A roaming heavyweight, moving on slow, powerful tail beats from one warm sea to the next. So what does that really mean? Let's slow down and spell it out. Megalodon was a global roamer, but probably a local napper. That's not poetic, it's biological. It could cross oceans when it needed to, but it didn't just wander for no reason. These sharks followed patterns. Warm currents, whale migrations, breeding seasons, feeding grounds, nursery zones. It had its hotspots: coastal shallows, continental shelves, and mid-ocean ridges where prey was abundant and competition was manageable. It probably returned to the same places seasonally, just like many whales do today. Long journeys, yes, but with a reason. Fossil teeth back this up. You don't just find megalodon remains randomly. They cluster in predictable bands: coastal deposits, riverbeds that used to be ancient estuaries, old seafloor sediments now pushed up into cliffs and fossil beds. Some places, like the coastal waters off North Carolina, Peru, and Morocco, yield teeth in huge numbers. That tells you something. These weren't just pass-through zones. They were core zones, prime hunting or birthing waters. But megalodon wasn't restricted to those regions. It followed warm water belts across the globe, from the Atlantic to the Indian Ocean, from the Caribbean to the Pacific. It had no continent. It belonged to the sea. That's not a romantic notion. It's supported by paleoclimate modeling. During the Miocene and early Pliocene, the Earth's average temperatures were warmer than today. Polar ice was minimal. Sea levels were higher. That meant more shallow water habitats, more inland seas, more migration corridors. Ideal conditions for a massive, slow-burning carnivore. But this range came with trade-offs. Let's talk thermoregulation. Megalodon was big enough that it probably practiced regional endothermy, keeping certain parts of its body, like its eyes and brain, slightly warmer than the surrounding water. Modern lamnid sharks, like great whites, makos, and salmon sharks, do this. It gives them better neural function, faster muscle response, and a broader thermal range. It also means megalodon could stray into cooler zones without shutting down. Not cold water. There's no evidence it swam under ice, but it wasn't limited to the equator either. Warm temperate zones worked fine. That expanded its range. Let it follow prey into new waters. That brings us to one of the most subtle but important parts of megalodon's life: energy efficiency. A 60-foot animal can't afford to sprint all the time. It has to cruise. Think of it like a glider, not a fighter jet. It probably swam at a steady pace of a few knots, covering huge distances each week with minimal effort. This isn't speculation, it's inferred from scaling models, muscle mass estimates, and hydrodynamic reconstructions. A shark that size can generate incredible thrust, but it pays a metabolic price every time it accelerates. So it didn't accelerate often. It drifted. It traveled far, but it did so slowly. There's that rhythm again: long calm periods, rare bursts of action. Now let's put this in motion. Imagine the shark migrating. The dry season hits in one hemisphere. A whale pod starts moving. Megalodon follows. Not aggressively, just with patience. Maybe it tracks a scent trail, or listens for low-frequency vocalizations. Or maybe it just remembers. Instinctively. The way turtles return to the same beach, the way salmon return to the same river. Eventually, it reaches the shallows off what is now Panama. Or perhaps Indonesia. Or the southern coast of Africa. There it hangs beneath the pod, sometimes for days, watching for the weak, the stragglers. Then a kill. A single bite. Maybe a second. A full meal. And after that? Digestion. Stillness. This rhythm could repeat itself every few weeks. Long-distance travel. A few high-energy kills. Then silence. That's how a global predator keeps going without burning out. Now, let's talk navigation. How did it find its way? No GPS. No sonar maps. But modern sharks can detect Earth's magnetic fields. Some even use the angle of the sun to orient themselves. Others pick up on water chemistry, temperature gradients, and current changes. There's no reason to think Megalodon didn't use all of these. It may have had a magnetic sense strong enough to feel the pull of oceanic ridges. Maybe it tracked heat gradients the way salmon track freshwater plumes. Or perhaps it remembered seamount chains and continental shelves like landmarks. Not consciously, just genetically coded memory. Instinct dressed up as wisdom. You might imagine it swimming through a warm current, head slightly tilted, feeling the pressure differences along its flanks. Adjusting, turning, never in a hurry, never unsure. That image is hard to shake, isn't it? Not scary, not aggressive, just certain. A being too big to be rushed. One more angle. How deep did Megalodon swim? Not to the abyss. Not to the twilight zone. It likely stayed in the upper few hundred meters of the ocean. That's where the prey was. That's where sunlight still filters down. That's where warm water pools and life congregates. But it could have followed dying whales into deeper zones, maybe 1,000 feet or more. Not routinely, but when it needed to. That's what its physiology suggests. Big liver for buoyancy control. Large eyes for low-light vision. Fat stores for energy reserves. But mostly, it stayed up high. Warm, lit waters. That's where the action was. That's where it was built to live. And that's how you should picture it now. Not racing. Not lunging. Just drifting across entire oceans. Month by month. Year by year. Tail sweeping side to side. Mouth closed. Eyes calm. Always moving. Never hurrying. The ultimate slow traveler. You're drifting just beneath the surface again. It's warm here. Open water, glassy calm. Sunlight filters down in soft beams. Below, something huge moves past. Not fast. Just steady. Effortless. It doesn't even have to notice you. Because nothing notices it first. This is what it means to be an apex predator. Not just big. Not just dangerous. But unquestioned. For millions of years, Megalodon didn't compete. It dominated. Let's talk about what that actually looked like. Megalodon wasn't just a big shark in a sea full of little fish. It was the defining presence in every ecosystem it entered. When it showed up, things moved. Not because it made noise, sharks don't, but because life around it learned, slowly, not to be in the way. You'll see this reflected in prey behavior, in fossil evidence, in migration patterns that shift subtly over time. Whale pods change routes. Small predators disappear from once busy hunting grounds. Not fast. Not dramatically. Just slowly. Quietly. Like everything in Megalodon's story. Its supremacy wasn't about being the flashiest predator in the water. It was about being the one thing nothing else wanted to mess with. Start with its sheer physical presence. A full-grown Megalodon was longer than a school bus, weighed more than a semi-truck, and moved like a submarine. It didn't hide. It didn't stalk from the shadows. It simply was. If you saw it, it was already too late. Then there's the bite. We've covered that upwards of 40,000 psi. But let's put that in perspective. That's strong enough to bite through a whale skull. To snap massive vertebrae. To cleave cartilage and bone in one motion. Other predators nip, drag, or chase. Megalodon just ended things. There's a rhythm to that kind of power. A slowness. An inevitability. It also shaped the ecosystem. In every habitat where Megalodon teeth are found, there's a familiar cast of characters. Medium-sized baleen whales. Toothed whales. Large fish. Sea turtles. And always, a few other big sharks. But not too many. Because Megalodon's presence put a ceiling on other predators. But because no one wants to compete with a 60-foot killer that doesn't get tired. It's not just about the food. It's about the space. Megalodon wasn't territorial the way mammals are, but it still dominated through sheer presence. Any area with enough prey to support a Megalodon probably couldn't also support multiple large competitors. So, over time, those competitors shrank. Changed tactics. And yes, there were a few exceptions. We'll get to those. But during its peak, Megalodon ruled. No debate. No rivals. Here's a fascinating detail. Some smaller sharks may have followed Megalodon the way remeras follow great whites today. Feeding on scraps. Staying just far enough behind to not be a threat. Benefiting from the kill without challenging the killer. It's not a bad strategy. Stay close. Stay small. Stay out of the way. Now let's talk about the way Megalodon's dominance expressed itself over time. Because it wasn't just a predator, it was an apex predator. The difference matters. A predator hunts. An apex predator shapes everything. The ecosystem forms around its patterns. Prey evolves not just to avoid being eaten, but to avoid being seen. It's a pressure that slowly alters everything else. How animals move, where they breed, how fast they grow, how they group. And because Megalodon was around for millions of years, that pressure lasted long enough to leave a mark on entire lineages. Whales started getting bigger, stronger, faster, not because of Megalodon alone, but its presence certainly helped speed things up. There's evidence that the rise of streamlined whale species coincides with periods of high Megalodon abundance. Now pause for a second. Zoom out. Imagine a world where one animal subtly reconfigures the behavior of dozens of others just by existing. Not through violence, just through potential violence. That's the real definition of top-tier dominance. You don't have to strike often. Everyone just knows what happens if you do. It's important to say, this dominance wasn't flashy. It was slow, boring even. There's no drama here. No climactic battles. Just a quiet kind of pressure. The way a mountain exerts force on the land around it, not suddenly, but inevitably. And yet, cracks began to show. It started with climate. Ocean temperatures cooled, just slightly at first. Then more. Slowly, currents shifted. Upwellings changed. Prey began to migrate differently. Not away from Megalodon, just elsewhere. But that still mattered, because it meant the predator had to travel farther, work harder, find new hunting grounds. That wasn't a death sentence. Megalodon was adaptable. But the cracks were forming. New predators emerged. Not bigger, but smarter, more social. We'll get to them. For now, remember this. Megalodon didn't lose its crown in a single moment. It held it for millions of years. Uncontested, undefeated. And that kind of reign doesn't end with a bang. It fades. Slowly, like a tide going out. But we're not at the fade yet. We're still in the golden stretch. When the shark that could kill anything did, rarely, efficiently, and with zero resistance. No challenge, no rush, just absolute confidence, moving silently through warm seas, while everything smaller moved out of its way. Let's change the pace. Very slightly. Because now we start to feel the first real resistance, not from other animals, but from the water itself. It's the Miocene, maybe 10 million years ago. Megalodon is still king, still enormous, still dominant. But the water isn't quite the same. Not warmer, but cooler. Not everywhere, just in places. Not fast, but noticeably. This is where the currents begin to shift. Subtle at first. Later, consequential. So what caused it? Start with plate tectonics. The continents were still slowly drifting, and those movements matter. Around this time, the Central American Seaway, what we now call the space between North and South America, began to close. The gap narrowed, inch by inch, until the Pacific and Atlantic were no longer fully connected the way they had been. This changed everything. Ocean currents are like conveyor belts. They carry heat, nutrients, and life across the globe. When you close a major seaway, you disrupt those conveyor belts. The Atlantic started to warm. The Pacific began to cool. Salinity shifted. Nutrient upwelling changed. And with it, the availability of prey. That's not a theory, it's visible in the sediment record. Diatom blooms dropped off in some areas. Fish populations shifted. Whales started altering their migration routes. Some areas that had been rich hunting grounds became less predictable. For a creature like Megalodon, that wasn't a crisis. But it was an adjustment. And that's the key word here, adjustment. Because everything that follows from here is exactly that. Nothing sudden. Nothing cinematic. Just a slow drag on the system. Here's another shift, global cooling. Around the late Miocene into the Pliocene, roughly 7 to 4 million years ago, the Earth started to cool more significantly. Ice sheets began forming at the poles. Seasonal temperature changes became more extreme. Sea levels dropped, ever so slightly. Remember, Megalodon liked warm, shallow seas, nursery areas, feeding grounds, continental shelves. But with sea levels falling, those ideal zones shrank. Some were cut off entirely, others became harder to reach. And the warm water bands Megalodon liked to roam? Those tightened. The shark didn't go extinct yet, but it had to work harder to find what used to come easy. Let's talk about temperature tolerance. Modern great whites can handle a wide range of temps. Thanks to regional endothermy, they hunt in both warm and cold waters. Megalodon likely had similar traits, but it still preferred warmth. It wasn't built for icy currents. It wasn't swimming under glaciers. So as cooler zones expanded, Megalodon's preferred range shrank. This pushed it into more competition, not with other predators, but with space. Less warm water meant more species crowding into the same hunting grounds. Prey and predator alike. More overlap. More stress. This is where the pressure begins to build. Another detail worth noting, upwelling zones. These are places where deep, cold, nutrient-rich water rises to the surface. They fuel food chains, support plankton blooms, which feed fish, which feed whales. Megalodon likely followed these zones closely. But as currents changed, upwellings became more unpredictable. Some vanished. Some shifted locations entirely. Imagine the map changing under you, year after year, generation after generation. Not catastrophically. Just enough to matter. A feeding ground disappears. A nursery warms too slowly. A prey route shifts west by 100 miles. Now multiply that by thousands of years. That's what was happening. You've probably picked up on the theme by now. Megalodon didn't lose a fight. It lost conditions. The very environment that had made it inevitable started moving in a different direction. And the shark couldn't move fast enough to keep up. Let's drill into the idea of energy balance. Megalodon was huge. That gave it many advantages: power, presence, thermal inertia. But it also came with cost. A big body requires more energy, more prey, more space. So when ocean productivity dropped, even just a bit, that imbalance started to show. In short, the shark needed more than the sea could now reliably give. This wasn't just a Megalodon problem. Many large marine animals felt the same squeeze. Some adapted, some moved, some shrank. But Megalodon? It was too big, too slow to change. Evolution doesn't turn on a dime. What does all this look like in the fossil record? Sparse layers, fewer teeth, wider gaps between finds. Regions that once produced dozens of specimens per site now yield just one or two. It's a quiet fade, a sign of dwindling numbers or of movement into less fossil-friendly waters. Either way, it tells the same story. The peak had passed. But remember, this didn't happen over centuries. It took hundreds of thousands of years. Long enough that Megalodon probably didn't feel its decline. It just lived differently, moved farther, waited longer between kills, maybe traveled alone more often, maybe stayed close to one last reliable coast, maybe followed one last migration route that hadn't changed yet. There's a loneliness to that picture, isn't there? A single giant predator gliding through open seas that feel just a little less welcoming every decade. Not hunted, not starving, just slightly out of step, but still holding on, still feeding, still birthing, still passing on its genes. For now, because even slow changes catch up eventually. But we're not there just yet. Right now, the currents are shifting, and Megalodon is adapting, even if only a little, drifting a bit farther, waiting a bit longer. And somewhere beneath the waves, a familiar shape moves through unfamiliar water. Slower, but still enormous. Picture a coastline. Not today's coastline, not even close. Think shallower, warmer, scattered with lagoons and inlets. Back then, sea levels were different. The continents weren't parked exactly where they are now. But the essential idea remains. The edge between land and sea, where young things begin. This is where Megalodon gave birth. Shallow nursery zones. Warm, protected, rich with prey. Not safe, exactly, nothing in nature truly is, but safer than the open ocean. Now imagine being born into that. You're not born small. Even as a pup, you're longer than most adult sharks. Maybe 6 or 7 feet. Already a predator, already capable of fending for yourself. But you're not ready for the open water. Not yet. You stay in the nursery, where the big threats don't usually reach. That was the system. For millions of years, it worked. But like everything else in this slow-motion story, that system started to fray. Let's walk through why. First, the geography. As sea levels dropped, remember the cooling we talked about in the last section? Some of those shallow nurseries disappeared. They dried up, or they shifted, or they cooled enough to stop supporting the same rich food webs that baby megalodons relied on. Second, prey changes. The fish and small whales that once flooded these safe zones began to thin out, or migrate, or evolve in ways that made them harder to catch. Some got faster. Some changed their seasonal patterns. Some simply stopped coming back. And third, the water itself. Temperature matters. Even small fluctuations, just a couple degrees, can change developmental success. Cooler water can slow growth, increase infant mortality, interfere with feeding. Megalodon pups needed warmth to thrive. When that warmth grew patchy or unreliable, survival rates likely dipped. We're not guessing. We know these nursery areas existed because of the fossil evidence. Clusters of smaller megalodon teeth show up in specific ancient coastal regions: Panama, the southeastern US, parts of Spain and Portugal. These weren't random juvenile deaths. They were places where young sharks stayed, grew, and eventually left. Until they couldn't anymore. Let's zoom in. Picture a young megalodon in what is now the coastal plains of North Carolina, maybe 5 million years ago. It glides through estuarine waters. The temperature is borderline, not cold, but not as warm as it used to be. Its usual prey, early dolphins, large fish, are less abundant. The shark is growing slower than it should. It's feeding less efficiently. It's burning energy just to maintain body heat. And it doesn't know why. Because this isn't a decision it can make. It's just born into a time when the conditions are no longer perfectly aligned. Now scale that problem up. Across populations. Across continents. That's how slow extinction happens. You don't need to lose the adults. You just need fewer juveniles to survive. Every generation is slightly smaller, slightly weaker, slightly less widespread, until, gradually, the whole species starts to thin out. Let's also talk about competition. Other predators were beginning to creep into those nursery zones. Not big ones, those stayed offshore, but medium-sized sharks. Opportunists. Maybe even early orcas. They weren't hunting megalodon pups directly, at least not often, but they were eating the same prey, creating stress in the food web, increasing pressure. And that changes the dynamics. Because megalodon pups didn't just need to grow, they needed to grow fast, to get big enough to survive in open water. If that process slowed, if they lingered too long in a now hostile nursery, mortality spiked. It's a death spiral, slow and quiet. We don't have evidence of mass die-offs. No fossil beds full of juvenile skeletons. That's not how this played out. Instead, we see absence. A fading signal. Once teeming nursery zones yielding fewer and fewer teeth in younger strata. Some researchers suggest the Mediterranean was once a nursery ground. But as salinity fluctuated and prey changed, even that fell off the map. Others point to the Indian Ocean, another warm, productive area, but again, the signs of juvenile megalodon activity taper off toward the Pliocene. It's the same pattern. Fewer safe places to start life. Fewer chances to reach adulthood. Fewer adults to make the next generation. And with that, fewer sharks, period. This is the part of extinction that's hardest to visualize. Because it's not about dramatic death. It's about non-birth. About absence. No new teeth. No new hunters. Just the quiet erosion of a population that no longer replenishes itself. What's remarkable is how long it took. A lesser species might have folded fast. But megalodon had inertia. Even as nursery zones failed, adults survived. They ranged farther, adapted in small ways, maybe gave birth in less optimal places. Maybe changed breeding seasons. Maybe switched diets just enough to hang on. But it wasn't sustainable. Not because of one thing, but because of dozens. All slow. All small. All adding up. It's like trying to grow an oak in soil that's slowly losing its nutrients. You can plant the seeds. Some will sprout. A few may even grow tall. But most won't. And over time, the forest thins, not from chopping or burning, but from the quiet inability to replace itself. That's what happened here. Megalodon didn't just die off. It failed to begin again. Its babies didn't become juveniles. Its juveniles didn't become adults. Its adults became lonely. And somewhere, in one of the last shallow bays that still felt familiar, the final generation was born. Bigger than anything around it. But with nowhere to go. Here's where things get a little more crowded. For millions of years, Megalodon had the top tier to itself. Nothing hunted it. Nothing really rivaled it. It wasn't just apex, it was alone at the apex. Big enough, fast enough, bitey enough to do what it wanted, when it wanted, across most of the warm oceans. But nature doesn't leave power gaps untouched forever. Let's talk about competitors. Not rivals in the Hollywood sense. No dramatic face-offs in the deep, but quiet, evolutionary interlopers. Species that didn't challenge Megalodon directly, but started eating its food. Messing with its ecosystem. Edging into its niche. First on that list, orcas. Or, to be precise, their ancestors. The earliest killer whales didn't look like today's. They were smaller, more varied, probably more like a mashup between dolphins and large predatory whales. But they had teeth, coordination, and intelligence, and they hunted in packs. That's a game changer. A single predator is powerful. But a group of smart predators? That shifts the whole calculus of survival. A lone megalodon could take down a whale, sure. But coordinated dolphin-like predators could harass prey in a different way, cutting them off, forcing them into shallows, splitting up pods, wearing them down. And these new hunters weren't limited to the giant adult whales Megalodon preferred. They could feast on calves, on mid-sized species, on anything too small or too agile for a 50-ton shark to chase. So while Megalodon was still king of the big kill, its hunting grounds were getting poached. It's like this. Imagine you're a lion that only hunts zebra. And suddenly, packs of wild dogs start taking down the young zebras before you can. You still win when you catch a full-grown one, but it happens less often. You burn more energy. You get hungrier more often. That's the pressure. And these orca ancestors weren't the only ones. Smaller shark species were diversifying. Some adapted to cooler waters. Some specialized in schooling fish or cephalopods. Others moved in and out of Megalodon territory, using reefs or coastlines to duck in and grab easy prey. None of these sharks threatened Megalodon directly. But all of them contributed to the same problem. Less food, more competition, thinner margins. Remember, this wasn't happening in a vacuum. Climate was still shifting. Sea levels still falling. Ocean currents still being rerouted. Every stressor we talked about in earlier sections, fewer nurseries, changing prey, was still in play. Competition didn't cause the extinction, but it accelerated the drag. Here's another twist, prey evolution. Whales weren't just shrinking in number. Some were getting smarter, faster, more maneuverable. Early baleen whales began migrating over longer distances. Toothed whales, like early sperm whales, started forming more complex social groups. That matters. A whale pod that learns to avoid certain coastal areas after a few ambushes? That's behavioral evolution. A calf that instinctively swims closer to mom in dangerous waters? That's a survival mechanism passed forward. Megalodon couldn't change that fast. Evolution moves slow. If your prey gets smarter and faster, and you don't adapt just as fast, you start to fall behind. Let's dwell on one particular species for a minute, Livyatan melvillei. Think of it as the ancient sperm whale's nightmare cousin. Around 12 to 10 million years ago, this thing was massive, maybe 50 to 60 feet long. It had giant, functional teeth in both jaws, unlike modern sperm whales, and it hunted other whales. Full-grown whales. This wasn't some distant scavenger. This was a contemporary of Megalodon, and likely a competitor. Both fed on the same things. Both patrolled the same waters. We don't know if they ever clashed directly, but even if they didn't, they were on a collision course in the food web. Over time, Leviathan seems to disappear from the fossil record, just like Megalodon eventually does. But for a stretch, the oceans had two enormous apex predators. One a shark, one a toothed whale, carving up the whale population between them. That's not sustainable. Prey can't keep up with two hyper-efficient top predators, especially when the environment is already shifting. So here we are, a moment in time when Megalodon is still huge, still alive, still capable of taking down a whale on its own. But it's not hunting in peace. The food is harder to find. Other hunters are showing up first, and the prey themselves are getting better at escape. Think about what that does to a species. It means more energy spent hunting, less success per chase, longer stretches between meals, fewer opportunities to breed, and higher stress while raising young. And when the next generation arrives, they're born into this already strained system. They're already behind. Now imagine that compounding over thousands of years. That's how big predators disappear. Not through battle, not through mass extinction events, but through 1,000 small, cumulative losses. Let's put it a different way. Megalodon was optimized for a specific world. Warm oceans, slow whales, plentiful food, minimal competition. As that world frayed, Megalodon didn't lose its place overnight. It just became slightly less efficient, then less again, and less again. And those small losses, uncorrected, eventually added up to failure. That's what competition looks like in deep time. Not a fight. A pressure. And that pressure was rising. Let's follow a whale. Not a blue whale. Those came later, but one of its early cousins. Smaller, sleeker, maybe 30 feet long, traveling in a pod. It's the Pliocene now, around 3 or 4 million years ago. The oceans have cooled a bit more. The currents are shifting. The water's more turbulent in places, clearer in others. And this whale swims differently. It's faster. Not lightning fast, but quick enough to outpace a large, lumbering predator over distance. Its tail is stronger, its fluke more efficient. It travels in tighter groups, with more coordination. It knows when to dive, when to flee, maybe even when to fight back. Now think about the predator tailing it. Megalodon. Still massive. Still lethal. But starting to show its age, evolutionarily speaking. See, this is the tipping point. Not because Megalodon suddenly got worse at hunting, but because its prey steadily got better at escaping. Let's break that down. Megalodon's hunting strategy relied on brute force. It would ambush prey from below or the side, delivering a single, catastrophic bite, often targeting the chest or flippers, to immobilize. It didn't chase prey for long distances. It didn't need to. That initial strike was supposed to be enough. But if that prey accelerates just a little faster, if it detects the predator a split second sooner, if it swerves or rolls or pulls tighter into its pod, suddenly the one-strike strategy isn't so reliable. And remember, Megalodon was huge. 50 to 60 feet, tens of tons. You don't just pivot at that size. You don't corner well. You don't sprint. Everything about you is built for power over agility, which works until your prey gets agile. The Pliocene seas were full of these faster whales. Not just one species. Dozens. Dolphins were exploding in diversity too, creating entire branches of nimble, sonar-using, speed-based mammals. All of them evolved in a landscape where being slow meant dying. This was selective pressure in action. The slow got eaten. The fast passed on their genes. And Megalodon, stuck with its inherited bulk, couldn't change its body plan fast enough to keep up. So, what do you do when your food starts outrunning you? Maybe you adapt your strategy. You might try scavenging more, eating carcasses. But that has its own issues. Carcasses are rare, and everyone else wants them too. Smaller sharks, scavenger whales, even seabirds depending on the depth. Or you go after easier prey, slower, smaller whales. But those were becoming less common too. And smaller prey means smaller returns. A 50-ton shark can't survive off 800-pound dolphins. The energy input doesn't balance out. You could also try going after calves, young whales. And maybe Megalodon did. But guess what? The whale mothers got more protective. They started forming tighter circles. They moved their birthing grounds to colder waters, shallower bays, places where a massive shark couldn't follow without stranding itself. Every change had a counter-change. And this was the crux of it. While Megalodon's size once guaranteed dominance, it was now becoming a liability. Let's talk about energy budgets. Big animals need big meals. A Megalodon likely required thousands of pounds of food every day just to stay alive. Not to grow. Not to reproduce. Just to operate. That means regular, reliable, high-calorie kills. But if those kills become harder to land, even slightly, the whole system wobbles. Burn too much energy on failed hunts, and you dip into reserves. Miss too many meals, and you can't maintain body temperature. Don't eat enough fat-rich prey, and your reproductive systems falter. And then there's recovery time. A failed hunt isn't just a disappointment, it's a delay. Time not spent feeding is time not spent mating, or migrating, or healing from injury. It adds up. Slowly. Relentlessly. Imagine an older Megalodon, scarred from decades of ocean life. It used to catch whales with ease. Now, every hunt takes longer. Every chase is more desperate. It tries smaller prey more often, but the returns are meager. Its muscle mass begins to shrink. Its territory, once vast, becomes narrower. It takes fewer risks. That's not extinction. Not yet. But it's the slow fade toward it. We can see echoes of this in the fossil record. The frequency of Megalodon teeth drops over time. Not instantly. Gradually. And the largest teeth, those from the oldest, biggest individuals, become rarer first. That suggests fewer successful adults reaching full size. Fewer thriving predators. You might think, well, why didn't Megalodon just evolve smaller? Adapt. Good question. Evolution doesn't work on demand. It doesn't shrink a species just because conditions change. It needs time, selection pressure, and a reproductive cycle short enough to allow for rapid change. Megalodon didn't have that luxury. With a likely long gestation period, slow maturation, and low reproductive output, it simply couldn't keep pace with the environmental and ecological changes happening around it. So it was locked in. Too big to fail until it did. Meanwhile, the competition, smaller sharks, toothed whales, agile predators, kept rising. They bred faster, adapted quicker, took over prey niches that Megalodon couldn't reach. And the whales? They just kept swimming. Faster, smarter, more elusive with each passing generation. By the late Pliocene, Megalodon wasn't the king anymore. It was a relic, a giant still capable of terrifying violence, but out of step with its time. A predator built for a world that no longer existed. And the whales? They didn't just survive Megalodon. They outlasted it. Here's what happens when the buffet runs out. You've got this enormous predator, Megalodon, built like a freight train with teeth, and it's designed to eat big. Big whales, big chunks of meat, big returns on every bite. But now, that kind of prey? It's getting harder to find. We're still in the Pliocene. The world's cooler than it used to be. Ocean currents have reorganized. Some shallow seas are drying up. The coastlines have shifted, and marine life is shifting with them. Whale populations, the large, slow ones that Megalodon once picked off with brutal efficiency, are declining. Not vanishing, but thinning out. Migrating farther. Breeding in colder waters. Calves are better protected. Pods are tighter. Adults are faster. What this means for Megalodon, the days of easy feeding are over. And sharks that size don't downsize easily. There's no light version of a Megalodon that can switch to krill or tuna. Evolution doesn't hand you a backup plan overnight. Now, a few things probably happened in parallel. First, some individuals may have tried to adapt. Maybe some went after smaller prey, mid-sized dolphins, seals, sea cows. That works for a while. But it's a losing game long-term. The energy output for hunting smaller prey doesn't come close to the calories a giant shark needs just to keep moving, let alone breed or grow. Second, breeding grounds may have started to fail. A shark like Megalodon doesn't give birth like a guppy. Its pups were born large, perhaps 6 to 10 feet long, and probably needed shallow, warm nursery areas to survive their early months. As coastlines changed and water temperatures dropped, those nurseries likely got rarer, or more dangerous, or disappeared entirely. Fewer pups, fewer replacements. And then there's the food chain math. Let's do a little thought experiment. Say a mature megalodon needs 2,500 pounds of meat per day. That's a rough guess, but it's based on estimates from modern great whites and scaled up for size. That's nearly a small whale a week, minimum. Now shrink the whale population. Spread them farther apart. Make them harder to catch. Add new predators into the mix. Early orcas, scavenging sharks, other toothed whales, all going after the same prey. Suddenly that weekly whale isn't guaranteed. You burn more energy looking. You fail more often. And that starts a slow decline that spirals. Less food, weaker individuals, lower birth rates, higher juvenile mortality. It's not a dramatic extinction. It's starvation by 1,000 logistical cuts. Fossil evidence backs this up, subtly. We don't find megalodon remains everywhere in late Pliocene deposits. In fact, they taper off, geographically and chronologically. The teeth we do find suggest smaller individuals were more common toward the end. Maybe that's because the giants weren't surviving to full maturity. Or maybe the entire species was skewing smaller under nutritional pressure. And here's a detail worth pausing on, the North Pacific. Some researchers believe this region was one of megalodon's final strongholds. Warmer waters, rich ecosystems, plenty of marine mammals. But even there, the fossil trail thins out after about 2.6 million years ago. That's not random. That's a pattern. One last thing to consider, this shrinking buffet wasn't just about whales. The entire marine food web was being restructured. Fish populations changed. Coral systems suffered. Upwelling zones, where nutrient-rich water rises to the surface, shifted locations. That affects everything from plankton to tuna to the animals that eat the animals that eat the animals Megalodon depended on. Think of it as the floor collapsing under the banquet table. The meal didn't just disappear. The whole restaurant shut down. You can also flip this from the other angle. What happens when a top predator disappears? You'd expect the food it once ate to boom. But that's not really what we see. There's no explosion in whale populations after Megalodon fades out. Because those whales were already stressed. Already shrinking. Already evolving out of Megalodon's range. Its extinction wasn't a release valve for prey. It was a symptom of a deeper shift. And once you zoom out, that shift looks global. Climate, currents, coastlines, prey, competition. Every system Megalodon relied on was in motion, and none of that motion was going in the shark's favor. So yes, Megalodon got smaller, at least as a trend. Not overnight, not universally. But over time, fewer giants, more medium-sized survivors trying to hold on. That's always the final chapter for a lineage under pressure. First, the range shrinks. Then the body size. Then the numbers. And then, nothing. Just teeth in sediment. Gaps in the fossil record. A ripple that fades. No mass extinction. No single moment of catastrophe. Just a big predator with no prey, no plan B, and no way to keep up. Let's stare into the dirt for a while. Not metaphorically. Literally. Because when it comes to Megalodon, nearly everything we know, its size, its diet, its timeline, comes from one thing. Teeth. That's it. Not bones. Not skulls. Not skeletons. Just teeth. Cartilage, the stuff that made up Megalodon's skeleton, doesn't fossilize well. It breaks down. Vanishes. Gets erased by time. But teeth? Teeth are different. Dense, mineralized, rugged. They last. So when we say the fossil record of Megalodon, we're really talking about a trail of teeth scattered across millions of years and thousands of miles. From cliffs in California to riverbeds in Morocco, from the seafloor off the Carolinas to the deserts of Peru. Teeth show up, and we read them like a sleep-inducing detective novel. And here's the pattern. Early on, Megalodon teeth are everywhere. Thick, wide, serrated blades, some as big as your hand. You find them in Miocene rock layers, 20 million years ago, give or take. All over the place. Then time rolls forward, and those teeth become less common. By the late Miocene, they're still showing up, but not in the same volume. Not in the same global spread. Some areas go quiet. Some sizes disappear. By the mid-Pliocene, around 3 million years ago, the record thins out drastically. In a few regions, it stops altogether. You don't need a catastrophe for that. You just need time, pressure, and a slow unraveling. The fossil fade isn't unique to Megalodon. It's how most extinctions look. There's no explosion, no final tomb. Just a gradual disappearance of signs. But it does raise questions. Was it really a slow extinction everywhere? Or did pockets of Megalodon survive longer in isolated regions? We don't know. The fossil record isn't a video. It's a series of snapshots, out of order, with most of the pages missing. One region might show a final Megalodon tooth at 3.6 million years ago. Another might have one dated to 2.7. Which one's the last? Impossible to say. Some researchers have tried to pin down a hard extinction date. 2.6 million years ago is the usual candidate. That's right around the Pliocene-Pleistocene boundary when big environmental changes kicked in. But others think Megalodon may have hung on a little longer in some warm, sheltered pockets. Even if that's true, the trend is clear. Megalodon teeth become rare, then absent. But it's not just the quantity that changes, it's the context. Earlier Megalodon teeth often show up alongside a rich diversity of marine mammals, whales, dolphins, seals. As you move forward in time, that association fades. You find Megalodon teeth in isolation, or near smaller species, or in areas where the big whale fossils are conspicuously missing. That tells us something about the world they were living in, or trying to. And then there's the vertical story, how deep in the rock layers those teeth sit. Go down deep enough, you hit thick bands of Miocene sediment packed with marine fossils. Megalodon included. But climb higher, newer layers, and they're gone. You hit Pleistocene strata, rich in other shark species, other whales, even early orcas. But no Megalodon. That's not an accident. That's extinction made visible. Of course, there are always false alarms. Every few years, someone claims to have found a late Megalodon tooth. A fossil that's too high in the layers. Too young. Some turn out to be misdated. Others are reworked. That is, older fossils moved by erosion into younger sediment. It's a reminder of how slippery this business is. And yet, for all the uncertainty, the pattern is unmistakable. The fossil record doesn't lie. It whispers. Softly. With gaps. But if you listen long enough, it tells you what's missing. And for Megalodon, it tells the same story over and over. Once widespread, then scattered, then gone. It's not dramatic. It's not cinematic. It's just entropy played out in layers of silt and time. What about the teeth themselves? There's a quiet trend there too. Earlier specimens, Miocene era, tend to be bigger on average. Broader, with deeper serrations. Later teeth, when you find them, often lean smaller. Narrower, possibly from smaller individuals, or maybe just juveniles. Either way, the implication is the same. The giants were vanishing. We don't find bite marks on late Pliocene whale bones that match Megalodon's tooth profile. We don't find nursery areas that clearly belong to them after 3 million years ago. It's like they stepped off the stage without applause. And here's the part that really underscores how final it is. No descendant species. No offshoots. No smaller sharks that clearly inherited the Megalodon legacy. The genus ends. The whole evolutionary line just stops. Contrast that with modern great whites, who still have cousins, ancestors, offshoots. Megalodon? Dead end. Its extinction, plain and quiet. Not the kind that comes with a bang. The kind that fades, like a shadow at dusk. And then you're left with the teeth. Lodged in riverbanks. Buried in coastal cliffs. Sold in shops. Studied in labs. Hung on necklaces. All that's left of an animal that once ruled the oceans. Each tooth is a timestamp, a remnant, a monument to a giant that outgrew its world. And the fossil record, for all its gaps, is clear about this. Megalodon didn't go out fighting. It went out fading. This is not a story with a bang. There's no asteroid, no supervolcano, no apocalyptic event that wiped Megalodon from the seas in one bad afternoon. What happened was slower, quieter, more like an engine sputtering out over miles of open water. A long fade instead of a final crash. You already know the pieces: cooling oceans, shifting coastlines, nursery habitats disappearing, prey getting faster or scarcer, new predators moving in. But here's the thing. None of those changes on their own were catastrophic. What made them fatal was how they layered on top of each other. If Megalodon had lost only one thing, say, its favorite whale species, it might have adapted. Maybe, but not when everything else was slipping out from under it at the same time. The late Pliocene was a threshold moment. Global temperatures continued to drop. The polar ice sheets were expanding. Sea levels began to fall, not dramatically, but steadily. That reshaped the shallow seas, the warm coastal areas, the estuaries and continental shelves Megalodon pups may have depended on. At the same time, migratory whale populations were adapting to cooler climates. That meant breeding in colder waters Megalodon, a warm water shark, likely avoided. The buffet moved, and Megalodon couldn't follow. Add to that the growing presence of competitors. Early orcas were more than just annoying little dolphins with attitude. They were becoming real threats. Not necessarily to adult megalodons, but to juveniles. And especially to Megalodon's ecological niche, the large prey specialist. Orcas were clever, cooperative hunters. They could take down smaller whales. They could harass larger ones. They didn't need to be bigger than Megalodon. They just needed to be smarter, more flexible, and harder to predict. Evolution doesn't reward size forever. It rewards adaptability. And that's where Megalodon came up short. It was a titan designed for a world that was already vanishing. Its strengths, size, bite force, thermal preference, became liabilities as the oceans changed. Even the physical evidence starts to look like a retreat. Teeth become rare. The regions where they're found become fewer. There's no last known megalodon. Just a point after which none appear. And it's not just that Megalodon vanished. It's how the world kept turning afterward. The marine ecosystem didn't collapse. It evolved. Orcas expanded. New species of toothed whales diversified. Other large sharks, like the great white, held their ground or shifted their diets. The niche Megalodon once dominated was absorbed, split, reshaped. You'd think the extinction of the largest predator in the ocean would cause a ripple, a cascade, some visible hole. But nope. The ocean simply moved on. That's extinction for you, especially the slow kind. It doesn't come with fire and ash. It comes with absence, with nothing. And then, just like that, one day the world exists without the thing it used to have. And here's the kicker, we almost missed it. If Megalodon's teeth hadn't fossilized so well, we might not even know it existed. No skeletons. No preserved jaws. Just these triangular fossils, popping out of riverbeds and cliff sides. Like geological hints of something enormous that slipped through the cracks. It's hard to wrap your head around that. A creature 50 feet long, ruling the oceans for millions of years, blinking out without a trace beyond some shed teeth. But that's what happened. It's not romantic. It's not tragic. It's barely even interesting in the big picture sense. Just a slow, inevitable end. A result of being too big, too specialized, too late. There's no villain. No single bad day. Just time, erosion, and evolution doing what they always do. Sanding down the edges, cutting loose what doesn't fit anymore. By the time humans showed up with boats and stories of sea monsters, Megalodon had already been gone for 2 million years. We never saw it. We never feared it. All we have are its teeth, and some guesses. That's what makes its extinction so different from other prehistoric endings. No extinction layer. No shocked fossils. No smoking gun. Just silence. The kind of silence that doesn't announce itself. The kind that arrives unnoticed, over generations, until you realize one day that the ocean feels a little emptier. That's the shape of Megalodon's end. Not fire, not flood, just the lights going out on a giant with no one watching. So what's left? Not much, and that's kind of the point. Megalodon doesn't leave behind a legacy in the traditional sense. There's no direct descendant still swimming around. No evolutionary offshoot still carrying the torch. It went extinct and the line ended with it. Full stop. But it did leave something behind, just not in flesh and blood. It left impressions. Shadows in the fossil record. A trail of teeth scattered in layers of earth and seabed. Evidence that something enormous used to be here. And people noticed. Eventually. Early collectors in the 1600s didn't know what to make of the massive triangular fossils washing up on beaches or dug from cliff faces. Some thought they were tongues of dragons, turned to stone. Others said they were thunderbolts. It wasn't until the 19th century that paleontologists started fitting the pieces together, literally. They studied the shape of the serrations, compared them to modern sharks, and realized what they were looking at. Teeth from the largest predatory fish that had ever existed. But here's where it gets messy. What exactly was Megalodon? For over a century, it was filed under Carcharodon megalodon, basically a supersized ancestor of the modern great white. That made intuitive sense. The teeth looked similar, just way bigger. But as more fossils turned up and more comparisons were made, the story shifted. The serrations were different. The root structure was different. The path of evolutionary changes didn't line up cleanly. So scientists moved it. Now it sits in Carcharocles megalodon, part of an extinct branch of sharks that split off from the line that gave rise to modern great whites. Same family tree, different branch. That might sound like a technical detail, and it is, but it matters. It reminds us how much of paleontology is built on fragments, and how our understanding of these creatures can shift with every new find. With Megalodon, the puzzle will never be fully finished. We're always working with missing corners. And yet the public fascination with Megalodon endures, probably because of the scale. This wasn't just a big shark. It was absurdly big, 60 feet, some say. 3 times the size of a great white. Jaws wide enough to swallow a car whole. That kind of bigness sticks in the imagination. So even as the fossil record goes quiet, the cultural footprint grows louder. Books, documentaries, movies. Discovery Channel specials. Conspiracy theories about it still lurking in the deep. Every few years, someone shares a blurry photo or a sonar blip and says, could it still be out there? It's gone. But the myth lingers. In a way, Megalodon's legacy lives more in fiction than fact. It's the monster that once was. The real-life sea beast that doesn't need to be exaggerated, just described accurately, to sound unbelievable. Still, the real scientific legacy is in the rocks. Those scattered teeth are more than souvenirs. They're data points. Markers that tell us about ocean temperatures, prey populations, geological layers. Where the teeth are found tells us where warm seas used to flow. How their shape tells us what prey Megalodon hunted. How deep they're buried tells us when. Every fossilized tooth is a timestamp and a map. And by tracking them, we've learned not just about Megalodon, but about the world it lived in. A world that no longer exists. That's what makes its fossil record valuable. Not just because it's rare or cool or massive, but because it helps us understand change. Oceanic, climatic, ecological. You can trace entire epochs by when Megalodon shows up and when it disappears. Even in extinction, it has a role to play. There's also the cautionary tale aspect. Megalodon didn't die because of a single, sudden event. It died because its world changed too much, and it couldn't keep up. Too big, too specialized, too late to adapt. That story isn't unique. It's the story of most extinct giants. The massive marine reptiles of the Cretaceous. The mammoths and mastodons of the Ice Age. The more specialized, the more fragile. Megalodon wasn't weak. It was just built for a version of the ocean that stopped existing. And in that sense, its legacy is a reminder. Dominance doesn't guarantee survival. Scale can become a trap. Adaptability beats size in the long game. But beyond all that analysis, beyond the charts and strata and comparative anatomy, Megalodon's real mark is the space it leaves behind. That mental space where we imagine what it must have been like to share the ocean with something that big, something that ancient, something that, in its time, was unstoppable. That's not something we see in the fossil record. That's something we feel. Because even though the rocks go silent and the sediment buries the evidence, the idea of Megalodon stays with us. The teeth, scattered and weathered, are its last fingerprints. And they still show up. In streams. In cliffs. On dusty museum shelves. Tiny echoes of something enormous that no longer swims, but hasn't fully left. And now we're at the end of the road. You've followed this story across 20 million years. Watched Megalodon rise, feed, thrive, decline, and finally disappear. But the deeper you go, the more this turns into a mirror. Not just of a shark's history, but of how we think about time, survival, and the creatures we share the planet with. Let's pull it all together. We started with a lineage of sharks adapting, evolving, outgrowing their ancestors. Generation by generation, they became more specialized, more dominant, more terrifying. By the Miocene, Megalodon ruled the seas. Not with competition, but by towering over everything else in the water. Its design was genius for the time. Enormous jaws lined with serrated blades. A body capable of migrating across oceans. Blood-warmed muscles that let it hunt in temperate zones. It wasn't just big, it was efficient. Ruthlessly so. But success like that is a gamble. Every adaptation is a bet on the environment staying roughly the same. If the prey stays plentiful, if the climate stays warm, if nursery habitats remain stable, then a creature like Megalodon wins, again and again. But when the variables shift, suddenly, that specialization becomes a weight. And that's exactly what happened. The Pliocene didn't arrive like a thunderclap, it crept in. The world cooled. Whale behavior changed. Ocean currents danced to a new tune. Competitors showed up, smaller but smarter. And Megalodon couldn't pivot. It wasn't fast enough to outcompete the newer hunters. It wasn't flexible enough to downsize. It wasn't built to chase prey into colder waters or defend its nurseries from encroaching threats. So, over time, it just faded. And that's what makes its story quietly unsettling. Not because it was a monster, but because it wasn't. It was an apex predator that did everything right, until the world rewrote the rules. No explosion, no catastrophe, just entropy. And yet, we still can't let it go. You feel it, don't you? Even lying here, eyes closed, drifting towards sleep. There's a part of your brain still picturing that silhouette, 30 tons of muscle and instinct, gliding just below the surface. Because Megalodon triggers something deep. Deeper than fear. Deeper than fascination. It's the idea that the ocean, even now, might still be hiding something that big. That ancient. That real. But no. It's gone. What's left is this. A few thousand fossil teeth. A handful of vertebrae. And an echo. A long, slow rumble through geologic time. Its extinction was not an event. It was a process. One that spanned thousands of years and ended without applause. But the impression it left? That stayed. It lives in museum displays. In speculative documentaries. In the quiet shiver that comes when you look into deep water and wonder what once swam there. And now, it lives in your memory too. Not as a monster. Not as a myth. But as a reminder that everything, no matter how big, powerful, or invincible it seems, has a last day. Even the ocean has ghosts. So now, as the current slows, let the image settle. The ocean is calm again. The surface unbroken. Below, nothing stirs that remembers Megalodon. Not really. The world it ruled has folded into history, layer by layer, grain by grain. All that's left are traces, fragments shaped like teeth, washed smooth by time. You've followed the trail across continents and ages. Watched it sharpen, rise, fade. And now, you're left with silence. No need to chase anything now. Let the lights dim further. Let the tide pull you gently under, not in fear, but in quiet. The kind of quiet that only comes when the big questions have all been asked and the answers don't matter anymore. This wasn't a story about monsters. It was about timing, adaptation, and what it means to be the biggest thing in a world that refuses to stay still. Out there, the sea continues without Megalodon. Just waves, currents, shoals of smaller fish and other predators, none quite so large, none quite so final. And you? You're safe on the shore or floating just above sleep. Let your mind drift, unhooked from detail. Let the last images dissolve. Teeth in sand, shadows in deep water. Time layered like silt across the bottom of everything. It's over now. The predator is gone. The ocean has moved on. And so can you. Good night.